Hey guys, this is week six? Six? I don't know anymore. Anyways, this is the week after last week. And I am going to be going over a little bit of the gas laws today. So I am going to be kind of going over the relationship between the variables, and then in a second video, and it's only going to be a second video, not because of time necessarily, but because of the fact that I want to be able to work out some problems on my iPad. In the second video, we're going to learn about how to calculate things with gas laws. Charge your calculators. All right, cool. So let's go over the basics of what we kind of learned about the kinetic molecular theory, okay? So the relationship exists between gas particles, or the relationship that exists there is that kind of the amount of space they occupy is dependent on how much kinetic energy they have. So if particles of a gas are very, very cool in temperature, meaning they don't have a lot of kinetic energy, sorry, there's a paw reaching under my door trying to get in, just distracted me for a second. If there is not very much kinetic energy, then the particles are moving around very slowly, and therefore they don't collide as often, and therefore they're not going to increase pressure as frequently, and they're not going to need to expand volume as a result, okay? So the idea there being that the more kinetic energy you have, the more the particles are moving around, and the more collisions you're going to have, which could lead to pressure, okay? So the basic ideas there are we're talking about relationships between pressure, volume, and temperature. So what I'm going to kind of do here with a marker that works is create a little chart here. So pressure, volume, temperature, and then pressure, volume, temperature. Boo, boo, boo. Probably should have created this before I started filming, but you know, I don't care. All right. So the idea I have here is just a basic pressure, volume, temperature type of situation. So we said obviously pressure isn't going to affect pressure, volume isn't going to affect volume, temperature isn't going to affect temperature. So I crossed those out, okay? And so the idea there being the pressure has a direct relationship with temperature, meaning that as pressure goes up, temperature goes up. So I'm going to use my red marker for that. So no. So it has a direct relationship. I'm putting D for direct. That means as one does something, so direct means as one goes up, the other goes up. The opposite of that would be indirect, meaning as one goes up, the other goes down. Okay? So that's how I'm just going to kind of fill out this chart. I would probably recommend maybe throwing this in your notes just because it is going to help you with the non-calculation questions about the relationship between pressure, volume, and temperature, so keep that in mind. So the pressure has a direct relationship with temperature, so as temperature goes up, the particles move around more frequently, they collide more frequently with each other as well as with their surroundings, and that leads to an increase in pressure. So pressure has an opposite relationship with volume, and you're going to see that in an activity that we're going to be looking at as well, okay? So pressure has an opposite relationship with volume. So that means they have an indirect relationship. So let's think about, sorry, I didn't get all my props ready. So if you're like me, and you have spent an absurd amount of time and money ordering things off Amazon during this time to try to make yourself happier, you may have a lot of these around, right? Okay? All right. So these are kind of they're literally just, they're just air pockets. Like they're just meant to kind of stop things. So what you can notice here is that if I just have it going, it doesn't seem like it's really fully inflated, right? There's a little bit of give to it, and so I'm able to kind of pinch it a little bit here and there. It's not completely inflated. So realize, of course, this is filled with air, so it's filled with the gas. Now, as I start to apply pressure to the outside of this, notice that it is starting to look very bulbous, okay? So what I'm doing here, I'm applying pressure to the outside, but I guess I shouldn't use that word. I'm applying force to the outside because what I'm doing is by squishing in a little bit, I'm decreasing the volume. So the gas is trying to escape from between my hands where it can't. And so, yes, it popped. I don't like loud sounds, and I also couldn't get it to pop, so it just, anyway. So what we saw there was as I started to squeeze it more and more and more, the air inside was increasing in its pressure because it was decreasing in volume. So it was trying to fix that problem. And the only way to fix that problem would be to say, okay, well, you're decreasing the volume. I have got to increase the volume to try to level this out. Because anything at high pressure, high temperature, etc., is not really a safe place for that substance. It's kind of just considered to be, I don't know, just kind of just a random situation for it. That's really not natural, if you will. So the idea there being that it wants to kind of overcome that. It wants to kind of fix the problem that you're creating. And so it's kind of like with balancing equations, how you put a 2 here, okay, well that fixes that, but now you've created another problem, well fix it, right? So with gases, they kind of do the same thing. They try to overcome the problem that you've created for them, okay? I'm noticing on the screen that my mouth is moving at a different speed than I'm speaking, so if the video is weird, sorry. All right, so getting back to my chart, so it appears that I'm now on volume. So again, volume has an indirect relationship with pressure, and we already said that temperature and pressure have a direct relationship. Boop. So we have most of this table filled out already, essentially. So this means that temperature and pressure are directly related, no matter which one is being adjusted. So the way this is kind of saying is like, okay, this is the constant one, or this is kind of the independent variable, this is the dependent variable, if you will. So if I were changing the pressure, then it would have this indirect relationship with volume. If I were changing the volume, it would have an indirect relationship with pressure. So obviously it's the same thing, but I'm just kind of explaining how it's worked out. So volume and temperature are the last two. Now, again, temperature is kinetic energy. So if you increase kinetic energy, then they're going to expand a little bit. The particles are going to move around faster, and so that's going to cause them to kind of spread out within the container that they're in. And so the volume is going to expand. Now, if the volume is flexible, meaning it actually can change, then you're just going to see it expand like a balloon would. When you increase the temperature on a balloon or decrease it, it just kind of expands in and out. Now, obviously, if you increase the temperature of something that is a fixed volume and the gas is trying to expand, then it may cause it to rupture, such as this. I mean, obviously I poked a hole in it, but it would have popped if I had given it more time and effort. So even though it is slightly flexible, it is a fixed volume. It can't go much more than that actual volume. And balloons are the same way. Anyone who has ever had the horrifying experience of popping a balloon knows that they do, while the volume can change a little bit, there's only a certain range they can fit in. So it is going to be a situation where it's kind of, there's a maximum volume that you can actually reach. Oh, okay, the camera froze, so that's cute.